Hello friends, welcome back to my YouTube channel. This is 18th part of my discussion on liquid extraction, and I will continue my discussion on stage-wise liquid extraction. In part number 70, I had discussed the theoretical aspects of continuous multi-stage countercurrent liquid extraction, and here in this part number 18, I will be discussing a numerical that is based on continuous countercurrent multi-stage liquid extraction. As I said in part number 70, I had discussed how to find out the number of equilibrium stages that are required in countercurrent multi-stage liquid extraction, and then how to find out the minimum amount of solvent that is required in this operation. So today we will apply the theoretical concepts to find out number of stages, number of equilibrium stages, and minimum amount of solvent. So let us start the discussion. So I will be solving a numerical where I'll tell you how to find out number of equilibrium stages in continuous countercurrent multi-stage liquid extraction, and then how to find out minimum amount of solvent that can be used in this operation. To begin with, let us look at the numerical statement. Multi-stage countercurrent liquid extraction is used to extract acetic acid from its solution with water, and the feed solution contains 15% acetic acid and enters at a rate of 150 kg per hour. The solvent used is ethyl acetate and it enters at a rate of 80 kg per hour. The final raffinate composition is to be 2% or the final raffinate is to contain 2% of acetic acid in it. Find the number of equilibrium stages required in this operation. And the equilibrium data is given to us. So you have the solvent rich layer, composition of the solvent rich layer is given to us, and composition of the water rich layer is given to us. So you have percentage weight of A, percentage weight of B, percentage weight of C, and in water rich layer also the percentage weight of each of the three components is given to us. Percentage weight of A, percentage weight of B, and percentage weight of C. So, let us understand the numerical. A multi-stage countercurrent liquid extraction, it is to be used to extract acetic acid. So, in this case, solute is acetic acid. The solute that is to be extracted, it is acetic acid, and we denote that by capital C. So, it is to be extracted from its solution with water. So, water in this case is the carrier solvent, which we denote by capital A. The feed solution contains 15% acetic acid. Composition of the feed is given to us, and it enters at a rate of 150 kg per hour. The feed rate is given to us. The solvent used in this case is ethyl acetate, and we denote solvent by capital B, and it enters at a rate of 80 kg per hour. So the rate at which solvent is admitted into the operation, that is also given to us. It is 80 kg per hour. The final raffinate is to contain 2% of acetic acid in it. The final raffinate composition, it is also given to us. That is 2%. And based on this information, we have to find out the number of equilibrium stages required in the operation, and we will also find the minimum amount of solvent that can be used. Minimum amount of solvent that can be used in the operation. That also we will find. So there are two tasks. One is we will find the number of equilibrium stages, and then we will find the minimum amount of solvent that can be used in this operation. As I said, the equilibrium data is given to us where a composition of the solvent rich layer. Solvent rich layer is nothing but the extract layer, and water rich layer is nothing but the raffinate layer. So composition of extract and raffinate layers they are given to us. The compositions are given when the extract and raffinate phases are in equilibrium with each other. So you have a composition. So percentage weight of A, that is percentage weight of water in the extract phase, you have different values. And percentage weight of B in the extract phase, you have various values. And then various values for percentage weight of C in the extract phase, they are given to us. In the same way, we have percentage weights of all the three components in raffinate layer or water rich layer. Percentage weight of water, percentage weight of A is given to us, that is water. Percentage weight of B is given to us, that is the solvent, ethyl acetate, and percentage weight of C, that is also given to us. So these compositions for the solvent rich layer, that is extract layer, and water rich layer, the raffinate layer, when they are equilibrium with each other, then the composition of the three components in those two layers, these are given to us. And we are going to use this to find the number of stages, number of equilibrium stages that have to be used in order to bring about this extraction. And then we will also find out the minimum amount of solvent that can be used in this operation. So first of all, let us list the data that is given to us. The feed solution that is given to us, it is a solution of acetic acid and water. The rate at which it is admitted, it is given to us. It is 150 kg per hour. So F is 150 kg per hour. It is containing 15 weight % of acetic acid. That is composition of or concentration of the solute in the feed is given to us. It is XF. We denote that by XF. So therefore XF is 15 by 100. We are converting percentage value into weight fraction by dividing with 100. So XF is equal to 15 divided by 100. That is 0.15. Then the operation to be used is multi-stage counter-current liquid extraction. The solvent to be used is pure ethyl acetate, which means there is no any solute in it. It is pure ethyl acetate. So that means as per our notation, yn plus 1 is equal to 0. In order to know what are the notations, please, I'm sure you must have watched my previous video where I have explained all the notations that I have used. So since pure ethyl acetate is used as the solvent, yn plus 1 is 0. Then the rate at which solvent is admitted into the operation, that is given to us. So we denote that by Sn plus 1, it is 80 kg per hour. It is 80 kg per hour. The equilibrium data is given to us. So what is given? Composition in weight % of raffinate and extract phases when they are in equilibrium with each other. This composition is given to us. So raffinate in this case is water layer, as I said. Extract is nothing but the ethyl acetate layer. And the final raffinate composition is given to us. The final raffinate is to contain 2 weight % of acetic acid. So as per our notation, this is Xn. Xn, when you convert 2% to weight fraction, if you'll have to divide it with 100. So that will give us Xn as 0.02. And what are we supposed to find? What to find? We have to find out the number of equilibrium stages. This is one thing. And we will also find out the minimum amount of solvent that can be used. So second task for today is we will find minimum amount of solvent that can be used in the operation. So this is the given data, and we are supposed to find out the number of equilibrium stages and minimum amount of solvent that can be used in the operation. Okay, so let us solve the numerical. First, we need to convert the given data into an appropriate form which can be used to plot the required graphs. So we need nx, ny, x and y. So the data that is given to us, we will convert the data into this form. So what is nx? Nx is weight fraction of B in the raffinate phase. Ny, what is ny? Ny is weight fraction of B in the extract phase. Then small x is weight fraction of C in the raffinate phase, and small y is weight fraction of C in the extract phase. Now what is given to us? Here I am showing the table where I have converted the given data into this form. So percentage weight of B in the extract layer, that is solvent rich layer, it is given to us. So in order to convert percentage weight into fraction, I will have to divide the percentage value with 100, and that is what I have done. So 90, the extract layer, for example, has 97% weight of B in it. If I divide it with 100, I will get weight fraction of B in the extract layer. And then you have weight percentage of C in the extract layer. And when I divide it with 100, I will get weight fraction of C in the extract layer. Similarly, weight fraction of B in the raffinate layer, it is known to me. And if I divide it with 100, I will get weight fraction of B in the raffinate layer, that is Nx. Then I have percentage weight of C, that is known to me, and I'll divide these values with 100 to get weight fraction of C in the raffinate layer, that is small x. So in this way, percentage weight of B in the extract layer, it is converted to Ny by dividing the percentage value with 100. Percentage weight of C in the extract layer, it is converted to small y by dividing the percentage value with 100. Then percentage weight of B in the raffinate layer, it is converted to Nx, that is weight fraction of B in the raffinate layer, by dividing the percentage value with 100. And then percentage weight of C is converted into small x by dividing the percentage value with 100. So what we need Ny, Y, Nx and x. So we will be plotting Nx and Ny on the x-axis and x and y we will be plotting on the y-axis. So you are plotting nx versus corresponding x values, that is nx versus x, and then you are plotting ny versus y. So this ny is plotted against y, nx is plotted against x. Okay, now let us plot the curve. Okay, so after getting the required data, let us plot the graphs. We will be plotting two graphs. One is the ternary diagram, and the second one is distribution diagram. So for plotting ternary diagram, we will be plotting nx and ny on the x-axis and x and y on the y-axis. So if you plot the given values, you'll be getting the Bernoulli solubility curve. So this is the A-rich part of the curve, or you can say water-rich part of the curve, and this is B-rich part of the curve, or the ethyl acetate rich part of the curve. Then, as I said, we also need the distribution diagram, so we will also plot the distribution diagram. So distribution diagram is plotted by plotting, or the distribution diagram is obtained by plotting x on the x-axis and y on the y-axis. So you'll be getting the distribution curve in this way. So we need to use both graphs in our solution. So let us move ahead. Okay, so after plotting the graphs, next we have to locate points F and S n plus 1 on the ternary diagram. So ternary diagram is a plot of nx and ny versus x and y. So you get the Barnard solubility curve. Now we have to locate point F and Sn plus 1 on this diagram. Point F will be located at a point whose coordinates are xf0. So xf is weight fraction of C in the feed, whereas the weight fraction of B in the feed is 0. So that's why point F will be located at xf0. xf is 0.15. So point F will be located on the y-axis where x is equal to xf, that is 0.15. So it is over here, and we are going to call that point as point F. Then we have to locate point Sn plus 1. It will be located at yn plus 1 n by s, where yn plus 1 is weight fraction of C in the solvent and n by s is weight fraction of B in the solvent. And since you are using pure solvent, yn plus 1 is 0 as we are using pure solvent. Therefore, it will just contain B in it, and that's why n by s will be equal to 1. That means point Sn plus 1 will be located at 1, 0. That is, it will be located on the x-axis where n by s is equal to 1. So you have to locate at n by s is equal to 1. You will be having point S. After locating point S, the next task would be to connect F with Sn plus 4. Points F and Sn plus 1, they are connected by a straight line, and we have this straight line. So we have connected point F with the point Sn plus 1. Okay. Then the next task is to locate point M on the ternary diagram. So point M will be located at xm nm. Xm is weight fraction of C in the mixture, and nm is weight fraction of B in the mixture. But here we just need xm for locating point M. But first we need to find it. We don't know xm. So xm is given by this equation. Xm is equal to fxf plus Sn plus 1 into yn plus 1 divided by f plus Sn plus 1. So I have discussed this equation in my previous video. And now f is known to us, it is 150 kg per hour. Xf is known to us, it is 0.15. Sn plus 1 is known to us, it is 80 kg per hour. And yn plus 1, it is also known, it is 0. So if you use these values in the equation for xm, it will be xm is equal to 150 into 0.15 plus 80 into 0 divided by 150 plus 80. That is xm is equal to, if you solve this, xm will be 0.098. So xm point M will be located at x is equal to xm. So let us locate it. So xm is 0.098. So it is over here. And once you locate this point, once you locate xm, you go to the line fs where you have the intersection. That intersection point will be nothing but point M. So point M is located at x is equal to xm. Xm we got over here. It is 0.098. So it is over here xm, and then we are going to the line Fsn plus 1, and we are locating point M over there. Next is we have to locate the point Rn. Point Rn, it will be located with this coordinates xn, nn, where xn is weight fraction of C in it, C in the raffinate phase, and nn is weight fraction of B in the raffinate phase. That xn is known to us, It is given to us xn is 0.02 and we are going to use that to locate point Rn. So first of all, we will locate x is equal to 0.02. So it is over here, and then point Rn will be located on the A reach part of the binomial solubility curve. So point Rn will be located on the curve where xn is equal to 0.02. Then after locating Rn, we will draw a line from Rn that passes through here. So next task is we will draw a line that starts from Rn and then we will pass it through M, allow it to go and intersect the B reach part of the binodal solubility curve, and wherever the intersection occurs, we are going to name the intersection point as E1. So draw a line from Rn that passes through M, let it intersect with the B reach part of the curve, B reach part of the binodal solubility curve at E1. So I'll draw a line from Rn. I will allow it to pass through M, and then I will allow it to intersect with the B reach part of the curve, and now I will call this point as E. Then we will be drawing lines, two lines. One is Sn plus 1 Rn and E1F, and we will allow these two lines to intersect with each other, and the intersection point will be the difference point, that is delta. So first I will draw the line Sn plus 1 Rn. So the line Sn plus 1, it is passing through Rn, and then I am extending it for some distance, and then I will be drawing E1F. I will start at E1, allow the line to pass through F, and then allow the line to intersect with the previously drawn line. So I get this point, and this point is nothing but the difference point, and I am going to denote that point as delta R. Okay, so after locating delta R, next task is to find the number of stages. So we are going to get number of equilibrium stages. So let us learn how to get the number of equilibrium stages. So for this, we will need the distribution diagram which we have drawn earlier. So first thing is, I will look at the point E1 and read its y coordinate. So I am going to read the y coordinate of point E1. So it is around 0.21205, and then with this value y, I will go to the distribution diagram. I will locate that y on the y-axis, and then I will go to the equilibrium curve and get the value of x that is in equilibrium with the y that I have got from the ternary diagram. So I get this x. Now with the help of this x, I am going to locate point R1 on the ternary diagram. So when I come back to the ternary diagram, point R1 will be located at x is equal to 0.0099. So it is over here. And I will locate point R1 on the A reach part of the curve. So point R1 will be located over here. Now R1, the x that is used to locate R1 is in equilibrium with y that is used to locate E1. So that means these x and y, they are in equilibrium with each other. Therefore points R1 and E1, they will be connected by a tie line. This blue dashed line is the tie line that connects R1 and E1. Why we are connecting the 2 points with a tie line? Because the compositions that are represented by these points, they are in equilibrium with each other. Okay, so after completing this task, I will draw a line that originates at delta R, allow the line to pass through R1, and then allow it to intersect the B reach part of the curve, the intersection point will be E2. So I will start at delta R, draw a line, allow it to pass through R1. Then I will get the intersection point on the B reach part of the curve, and I am calling that point as E2. Then I will read the y coordinate of point E2, new y. With this y, I will go to the distribution diagram and find the corresponding x. So for this E2, for y2, that is representing point E2, here I will get x2, corresponding x2. So in this case, it is almost 0.05, and then I will use it to locate point R2 on the ternary diagram. So I'll locate 0.05, go to the A reach part of the curve, and then call that point as R2. Since R2 and E2, they represent compositions that are in equilibrium with each other, I will have to connect them with a tie line. This blue dashed line would be the second tie line that I have drawn in the process. After that, again I will start at delta R, draw a line, allow it to pass through R2, and then get its intersection on the B reach part of the curve. I will call that point as E3. So I get E3. Then for the E3, for point E3, I will read its y coordinate and then come back to the distribution diagram, and I will find, or I will get the corresponding x, and I will then use this x to locate point R3 on the ternary diagram. In this case, x3 is 0.005. It is 0.005. Sorry, it is 0.01. 0.01. So I will locate that x. So 0.01 is over here. Now the diagram is small, but let me tell you, you have to choose the scale in such a way that delta R should be located, because delta R is important. Without delta R, you will not be able to find the number of equilibrium stages. So you have to plot a graph with such scale which will allow you to locate delta R on the same page. That is important. So here the diagram is a little bit small, but you can see I have located R3 where x is 0.01. And then R3 and E3, they represent compositions that are in equilibrium with each other, and they have to be connected by a tie line. So in the process, what we have done, we have now the composition is below the final raffinate composition. Final raffinate composition is 0.02, and with the third tie line, we have reached a composition of 0.01. So once you go below xn, that is composition of the final raffinate phase, you have to stop. And the number of tie lines that you have drawn in this process, that will be the number of equilibrium stages that are required in the operation. So this is stage number 1, this is stage number 2, and this is stage number 3. So in this operation, 3 equilibrium stages are required. So the first thing is we need to plot the ternary diagram. The scale to be used, you have to select it appropriately so that you will be able to locate delta R. And then y values, for the y values that you read from the ternary diagram, you are finding corresponding x values from the distribution diagram. And then by using those x values, you are plotting, or you are locating various R's, R1, R2, R3. And R1 and even R's and E's that represent compositions that are in equilibrium with each other, those points will be connected with tie lines, and each tie line will represent an equilibrium stage. Number of tie lines that you draw in the process will be the number of equilibrium stages that are required in the operation. So I hope you must have understood how to get the number of equilibrium stages. If you have any doubt, you please mention that in the comment section. So in this case, in this operation, we need 3 equilibrium stages. So we are going to report the number of equilibrium stages as 3. So we need 3 equilibrium stages in this operation. Okay. Now, the next task, the second task. What is that? We have to find the minimum amount of solvent that can be used in this operation. So for this, I will have to use the same diagram, and for finding the minimum amount of solvent, we have to draw a tie line that passes through point F, and that tie line has to be drawn by trial and error by using the distribution diagram. So, if I take reference of the nearest given tie line, and then if I draw a tie line that is parallel to the nearest tie line through F, and then adjust it so that the end points of the tie line represents concentrations that are in equilibrium with each other. So what I am doing, I am drawing a tie line that is parallel to the nearest given tie line. I am drawing a tie line that passes through F, which is parallel to the nearest given tie line. But if you check the end points of this tie line, they will not be in equilibrium. They will not represent concentrations that are in equilibrium with each other. I have to adjust it. I have to adjust the tie line and make the end points represent equilibrium concentrations. So you have to do that by trial and error. So for me, the tie line with the end points, you have 0.12, 0.14 and 0.16. X 0.16 and Y 0.3. So these are equilibrium concentrations. So I will, by trial and error, I get a tie line which has the same points. X is 0.16. Let me show it properly. X is 0.16 and Y is 0.3. So I will draw a tie line with these end points. So this is the tie line. And I will extend the tie line so that it intersects the B reach part of the curve, and it also intersects the line Sn plus 1 Rnp going to delta R. So I get this point and I get this point. So I'm going to call this point as E1 M because it is representing E1 for the case of minimum solvent, and this delta R will be delta R for minimum solvent. So I'm calling that point as delta R minimum. I'm calling this point as delta R minimum. So after this, what I have to do, I will draw a line that starts from E1 M and meets RA. I have to draw a line E1 M RA. So if I draw it, I will be getting one intersection point, intersection with the line F S plus 1. So this is the intersection point. And that will give me M that corresponds to minimum solvent, and I am calling it as M minimum. And then I will read Y coordinate of this point that will give me X M minimum. XM for minimum amount of solvent. So in this case, XM minimum is 0.115. XM minimum is 0.115. So in order to get the minimum amount of solvent, what you have to do, you have to find out X yum minimum. And how to do that? First, you draw a tie line through F by trial and error with the help of this distribution diagram. To get its endpoint on the B reach part of the curve, call it E1 yum. Get its endpoint on the line Sn plus 1 Rn, call that as delta R minimum. Then draw a line from E1 yum to Rn. And in the process, you get a point where E1 yum and Rn line intersects with the line F Sn plus 1. Call that point as yum minimum. To get the y coordinate of this point yum minimum, that y coordinate is nothing but x yum minimum. Xm for xm corresponding to minimum amount of solvent. We are going to use this xm minimum to get the minimum amount of solvent. Okay, we got xm minimum, which is 0.115. Xm is given, we know the equation xm is equal to f into xf plus Sn plus 1 into yn plus 1 divided by f plus Sn plus 1. Now, if xm is replaced with xm minimum, s will be replaced with sbe. So, xm minimum is equal to f xf plus s minimum into yn plus 1 divided by f plus s minimum. F is known to us, F is 150 kg per hour, xf is 0.15 and yn plus 1 is 0. Ym plus 1 is 0 and let us use these values. So, it would be 0.115 is equal to 150 into 0.15 plus S minimum into 0 divided by 150 plus S minimum. That is 150 plus S minimum is equal to the numerator. When simply solve, it could give 22.5. So, 150 plus S minimum is equal to 22.5 divided by 0.115. So, this term I have taken to the other side and 0.115 is brought in the denominator. So, that is 150 plus S minimum is equal to 195.65. That is S minimum is equal to 195.65 minus 150. That is S minimum is equal to 45.65 kg per hour. So, in this way, we get the minimum amount of solvent that can be used in the operation. The rate is 45.65 kg per hour. This is the minimum rate of solvent that can be used in this operation. So, with this, I end my discussion for this numerical. Here you must have learned how to get the number of equilibrium stages in a typical continuous countercurrent multi-stage liquid extraction, and you must have also learned how to get the minimum amount of solvent that can be used in such a operation. So, if you have any doubts, you please mention them in the comment section. And with this, I will end my discussion for this video. Thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to it. And we will very soon meet in my next video. Till then, have a nice day. Bye bye.